So when we were putting together this program, we thought it might be a good time to just kind of assess kind of where we've been, what we've done, and kind of where we're at. So that's kind of what my next presentation is going to be about. So it's going to kind of give you a little bit of a historical view, as well as kind of where we've traveled, and then kind of where we are today, kind of what some of our challenges still are, and some places for future development as well. All right, so here's the beginning. I always like to have a nice picture on the front, and I'm always looking for like a cool piping picture or tanks or something like that. And this is one of my happy places. This is in Colorado, so I'm like, I came across that. It's like, I'm just gonna put that up there because, like I said, it's a place that I think is really cool. And so anyway, so it doesn't relate to FRP at all, but it's a fun place to go. All right, so again, so I'm going to kind of give you a little bit of history. We're going to talk about some of the early applications. We're going to talk about places where we have improved and advanced. We're going to talk about some of the markets and trends that have occurred over the years, as well as kind of give you an assessment of where we feel as Maverick, where the industry is today. And then also kind of talk about some potential places where we can grow as well. So, and what you see here, this is actually what they call a cable wrap tank. So this is basically pure FRP lining. You can see the nozzle there, and this is steel cables wrapped around the vessel on the shell, and you can actually still get these today. So, not real popular, but it's amazing. I think this one was probably almost 25 or 30 years old. So from a historical basis, one of the first corrosion-resistant pipes that was ever made was a wood stave pipe. And as you can see, Maverick was there. We were inspecting those pipes back in 1872. Now, our inspector, he's a little over 100 now. We had to retire him, but we have new inspectors now. And they're really good at FRP too. So some of the first FRP applications were in boats, as you can imagine, sailboats primarily, up in the Northeast. First pipes started coming out in about 1960 or so, when they saw that FRP worked so well for the boats. Started the pulp and paper mills, and they also started in the Northeast, and they're like, you know what, will that work for some of our bleach applications, some of our chlorine applications? Because it's all salts, is where it all comes from. So that's how FRP kind of migrated into heavy industry, and we started making pipes and tanks. As I mentioned, I do have a happy place in Colorado. I actually found this wood trestle out there. So this is another wood stave tank. It actually brings basically fresh water from a nearby reservoir out to a little town in the country about 10 miles away. Still works. Actually, as you can see, it's pretty high. I actually climbed up on the mountain where it crossed the mountaintop, and it was actually aligned with HDPE now. So it's still active, but they've integrated in some new technology as well. So I thought that was kind of interesting. I guess it's been about almost 10 years ago. My wife's family's from Croatia. We were on vacation, and I came across this tank. So it's a wooden tank. I mean, I always think about, I don't know if everybody's as old as me here, but there used to be a show, Petticoat Junction, and they would always have this water tank right next to the train station, and that's where it all started. So I always think about these wood stave tanks for those water tanks for the old steam engines. And by the way, you can still get that from Walmart. You can order it online. So if y'all need a wood stave tank, you can go to Walmart and find it. Back around the early 70s is when FRP started getting more mainstream, and there started to be more demands by industry. It started with desalination, water plants, and power utilities. And this is where FRP really started to kind of gain ground. Back in those days, a lot of it started to be, amazingly enough, they went right to large diameter. So like, it seemed like every 6 months, they were increasing size. They went from 6 foot diameter, 7 foot diameter, 8 foot, 10 foot diameter, 12 foot diameter FRP pipe. And they would go into service, and there was a lot of lessons learned. They would find that we have, I guess about 2 hours north of here is a plant in Crystal River, and it has an 84-inch FRP pipe that was installed in, I think, about 1980 or so. And they have a pants leg Y that comes out. So they take the seawater in from the Gulf, and it splits, and so it's an equal leg Y basically. And then it goes into one unit here and one unit here. And well, they had a failure in that. It just split right down the middle. So what do? We didn't call up an engineer and said, can we do some FEA on this and figure out what happened? It's like, okay, you know, come out and we need you to reinforce this. So it was adding more reinforcements, figuring out where the stress was. We would put basically FRP pipe stiffeners and braces on the inside of the pipe to make sure that it was going to stay stiff and square, because basically when it would see stress, basically it would flex, and that was what was ripping the joints. But there was a lot of advancement that was going on at that time. You know, what you see here, though, one here on the right hand or left hand side, this is 84-inch pipe that's coming in here. You've got 3 of them into 108-inch header. So this is a huge force, so this is all concrete encased here. The other side actually is Crystal River again. This is, the header was about, I guess almost half a mile long. I think it was over almost 40 cooling tower units, and went from 60-inch diameter on the low end to 108 on the high end. All FRP 36-inch risers coming off of it all the way down. So pretty impressive project, and quite a few lessons learned there as well. As we went along, we have had a lot of developments. Some of the early ones were in the resins. We went from polyester resins, isophthalic resins, into vinyl ester resins, bisphenol A resins. We have people from INEOS who can talk to all of these things, and basically improved corrosion resistance for, you know, salt applications, things like seawater service and things like that, all the way to, you know, sulfuric acid, hydrochloric acid, and at temperature too. So we had a lot of development there. Then as we got more questions about more demands, and we started getting into slurry, and we saw these in the power industry quite a bit. In the flue gas desulfurization systems, they basically transfer limestone slurries. And so we're getting a lot of wear, and this was happening in the metals too. So, hey, does FRP have an answer for this? So they figured it out. They started infusing silicon carbide into the resin, makes the liners harder, and it becomes resistant to the limestone slurry. And today we have other projects that are going on now. You've probably heard about like the lithium projects and rare earth elements and things like that. It's kind of the new technologies coming out. A lot of those handle slurries, so those kind of pipes are being used today as well. Then with respect to glass reinforcements, you know, Daryl and particularly Jose touched on all the different options for bales, for example. You know, we've learned over time that where we have a lot of like thermal shock and expansion, those carbon bales we tend to use a lot. So if we know that we're going to be seeing a lot of cycling, carbon bale tends to be a really good option in a lot of cases for something like that. It's really durable, very corrosion resistant as well. And then I guess it was probably about mid 90s to late 90s. Some of the glass manufacturers came out with e-glass that was corrosion resistant as well, and that's where we kind of moved to where basically the glass became corrosion resistant specifically for acids, not necessarily every surface. So like bleaches and things like that, it probably doesn't work quite as well. But for acids, it was particularly much more corrosion resistant. So that's kind of another development as well. We also found over time that the ECR glass actually had better mechanical properties. So even if we're not doing acids, we like to specify ECR glass because we know we're going to get better mechanicals on the lamins. And then, you know, you've seen some of the presentations already talking about filament winding, and we've you know, advanced that over time. We've got into custom laminates, like I think it was Jose that talked about like the 090 winding. So we've done specialty laminates for, we've built tanks up to almost 120 foot in diameter. And I've been asked, you know, well, is there a limit? And really the limit is really on the machinery. We need to develop a winder. We need to figure out how to basically to turn, if we go more than 120 foot, can we turn 150 foot? You know, it takes bigger machinery to turn it, and that's really what it comes down to. And then once we're done, so the 120 foot shell was right at about 600,000 pounds. So it's like, okay, it's on a mandrel, so they have to basically collapse the mandrel, pull the mandrel out, and lower the shell down to the ground, because the winder would put it about 3 foot off the ground. And you do that really slow. And it took about 2 weeks to actually lower it and actually set it on the foundation. Because basically they just chalked it up all the way around, and they just went around and pulled it out one chalk at a time, and it took about 2 weeks to do that. So we got creative and really expanded our kind of experience on what we can do. We've done chimney liners 40 foot in diameter by 1,000 foot tall for power plants, so which are pretty substantial, and they're supported and hung from the top, not from the bottom. So completely in tension, like a shower curtain almost. So when you go into it the first time, you're kind of gripping, kind of wondering, should I walk on this? You know, because it's a lot. I think some of the loads were almost 1 million pounds. So pretty cool stuff. So again, some of the manufacturing, we've done a lot with piping. We've understood, you know, kind of what makes it well. We talked about the custom winding. You know, basically, I think as Jose said, that 55-degree wind gives us that perfect 2-to-1 pressure envelope for the pipe. So we got basically twice the hoop strength as the axial strength. So, but if we wanted spans, we could move that to 45 for tanks. A lot of times you'll see we're going to 70, 75 degrees, because the hoop strength is more important, because it's just a static tank. There's no spans, and really it's just pressure containment is all we're worried about there. So for tanks, a lot of times we'll see the winding go to, you know, something like 70, 75, 80 degrees in diameter, or in wind angle rather. And you can see some of the sophistication here. Like this was one of the scrubbers that were built for, I think this was a carbon capture project. So a lot of nozzles, all nice and squared up, checked out, everything mates up, and the penetrations, there's a lot of high tolerance penetrations in there. Everything's got to come in nice and neat for it to work right. So we've learned a lot of good lessons over time. We've touched on dual laminates before. There are a lot of materials in dual laminates. I mean, you have everything from your polypropylene to PVC, CPVCs. You've got a whole host of fluoropolymers as well, PVDF, FEP, PFA, ECTFE, and they all have their sweet spot. As Daryl pointed to, whether it's material or it's a manufacturing process, really every material and every process or joint type has its place, and that's what we try to focus on. There's not like a good, better, best necessarily. It's because it's always a blend between the base is okay. You have a budget, you want quality, and your schedule. So some are faster, some are cheaper, some are better, but usually better costs more too. So there's a balance there. So you don't need to have the very best of everything all the time. And necessarily your budget isn't always the best all the time either. So you have to kind of find where's the middle ground where it meets my needs, but it doesn't necessarily, it may not be the best in everything, but you want to kind of get the best value out of what you're getting. And then we have, bonding techniques, welding techniques. When we look at dual laminates, we have, you've seen examples of hand welding. Oh, wrong button. There we go. You got hand welding like what you see here. There's also butt fusion welding. We see that a lot with like PVC and CPVC particularly. Those are, particularly CPVC is a harder material to weld by hand because it's a very hard material. It has a very narrow band of temperature that you have to work in, so you have to really control your parameters to do it well. And butt fusion the same way, but it's more automated. So basically you're taking two pipes like this, you have this hot plate in the middle that heats up to, I don't remember exactly, like 230 degrees, well probably more than that, more like 300 degrees or something. And basically it heats up both ends, they actually kind of mash it in, they pull it out, then they basically ram the two ends together, and that's their butt fusion joint. So they get it good and hot, and then they mash them together, and it's all temperature controlled, time controlled, the pressure's controlled, so that they're doing the same thing every time, and for every pipe size, that they have pre-settings so that they get that consistency out of it. So a lot of times we see that dual laminates tend to be more severe surfaces for where usually we're going to dual laminates where FRP, just straight FRP, is not a good solution. Usually it's a temperature limitation is what we see a lot of times, is that. Other times it may be a concentration issue where, say for sulfuric acid, FRP works great for 32 degrees sulfuric, but if it's at 93 degrees, it's not going to work well, and that might be somewhere we want to look at going to a dual laminate. Might even be somewhere where if it's something close to 97, 98, maybe even straight carbon steel works again. And like I said, from our view, we want to get the right material in the right place. We don't want to put FRP where it's going to be stretched and it's not going to do what is expected. It's not going to meet the customer's expectations. So that's knowing where those limits are. And basically, as kind of Daryl pointed out, is there's a lot of contributions from engineering and vendors and installation that you have to hit all those as well. Curing is a big point that we've learned quite a bit about. Generally, post-curing takes more time, and it's more expensive. Time is money, right? So, but what we've also found out, where surfaces are critical, if we cure it, we will move the mechanical properties from, say, 90%, 93% to 100%. We will drive the cure, all that. If you talk to Lisa here, she'll tell you all about cross-linking and stuff like that. And basically it drives that cure. So you maximize your mechanical properties, you also maximize the hardness and your corrosion resistance as well. So where we have those critical surfaces and those things are important to us, we know that, okay, well, we want these post-cured. You don't have to post-cure everything, but where we need that little extra and where we want to get to 20 years of life versus 16 or 17 years of life, because a few years is actually usually, in most cases, a few $1 million. So that doesn't sound like a lot, but if you have to rip it out that much earlier, it makes a big difference. And then permeation. When we're looking at the thermoplastics, all thermoplastics permeate, almost all materials permeate, even carbon steel permeates. Like hydrogen will go right through carbon steel. So it's knowing how fast each chemistry permeates through each material tells us how thick that liner needs to be. So it goes through FEP this fast, it goes through CPVC this fast, it goes through FRP this fast, okay? So with respect to thermoplastics, I think Alan was asking about like the lined steel tanks earlier. Thermoplastics, they all permeate and they will continue to permeate until they get the other side. It's just, is that going to be 5 years? Is it going to be 10 years? Is it going to be 25 years? That's the question. That's about the thickness of the material. Is it under pressure, or is this like ambient, like in a storage tank? all those things kind of matter. With FRP, it's similar, except FRP, the permeation generally stops. With the exception of chlorine, which chlorine kind of attacks everything, but if we're looking at sulfuric acid, we know sulfuric acid, if we have the right resin, will permeate about 20 to 30 mils. If we're looking at hydrochloric acid, that number is probably closer to 100 mils. That's why for sulfuric, we have a 100 mil liner, and 30 is plenty much that gives it pretty good margin for that. For HCl, well, we know it's going to go, almost 100 or so. So we put a 200 mil liner there. So that's how these choices are made. And they're all based on basically case histories as well as lab testing as also. So there's a lot that goes kind of behind that, and these are some of the things that we've learned as well. From an engineering standpoint, we've got improved standards. We've talked about NM2 is FRP standard for piping. There's NM1 for thermoplastics. We also have RTP1 for storage tanks and process vessels. And then we have Section 10 for pressure vessels over 15 PSI and up, I think they'll go up to 3,000 or even higher. Component design is an area that is getting a lot of attention these days, and we've learned quite a bit about. So if you are an engineer, whether the tank is steel or whether it's FRP, one of the questions that comes up is what are your allowable nozzle loads? And a lot of times they're like, well, we don't want any loads on our tank. Our tank is our tank, and we don't want you to put anything extra because it's not predictable. But the reality is, if you attach anything to a tank, there's a load. If you put an expansion joint on a tank, it takes a certain amount of activation load to actually compress that expansion joint so it actually works. And Rob can talk a lot about that. So we're seeing a lot of requests for nozzle load calculations after the fact, after they do their pipe stress analysis. Is this going to be okay? Do we need to add more lambda to a tank? Or as a vendor, we're seeing vendors being asked, what are your allowable nozzle loads on your vessels? And then what you see here similarly is what are the real loads in T's. We have done quite a bit of evaluations on that as well. Then when it comes to equipment, as I mentioned, we've done a lot of things with chimney liners, with tanks. We've learned over time that if we have a really tall tank, so the standards, basically it kind of is looking at a very stereotypical tank that's kind of twice as high as it is, and all the rules apply, nice and neat, no worries. Just follow the equations, it's cookbook, and everything works out fine. But if that tank is 3 times the diameter or 4 times the diameter, if it's 10 foot diameter and 40 foot tall, well, you've got more shell load coming down on that bottom knuckle, and now we really need to take a closer look at that bottom knuckle. So these are the kind of things that we've learned, because over time people have started seeing knuckles crack when that's not done. Why did this happen? And we do an FEA or some calculations, and we say, well, these loads on the knuckle are really high, so we really need to be reinforcing these quite a bit more. And then large diameter tanks, I mentioned, we've done some up to 120 foot diameter scrubbers. In some of the mineral processing, particularly 30, 40, 50 foot diameter tanks are pretty regular. They're doing very big processes. In some cases, those are built totally on site, where they do all the winding up and assembly on site. In some cases, what we do is we will blade it, and I don't think anybody there's not any fabricators here that do ablation. But basically they make a shell in the shop, and say that shell is 30 foot in diameter. Well, that's not going to go down the road. So you basically got to squeeze it down, so it goes from a round shell. They strategically squeeze it down so it's an oval then, and it will fit on a truck. Then they can ship it to wherever they want. Then I guess Thorpe does some of those now that I think, if I see you nodding back there. So they'll basically take it down the road, set it on the foundation again, re-expand it, and then they're basically setting in the bottom, cutting the nozzles, assembling the head, lifting usually it's like a pie-shaped kind of head that they're putting on top, and it's very effective. It's very effective. This is kind of what it looks like here when. So one of the things that makes it work is basically we do analysis just to show that when we collapse that shell, that it's going to be okay, because you can crack it if you don't do it right as well. So we're doing analysis on that as well. And then obviously stacks are kind of a whole different breed. So we've gotten really good, and pretty much from an FRP standpoint, we can design almost any kind of equipment as long as it's within the pressure requirements as well as the temperature requirements that meet for FRP materials. Pretty much, I would say that if you're in chemical processing, so like a non-wastewater application, almost every system needs to have pipe stress analysis thing, because we're usually running something like 50 to 110 psi, 150 psi system, and temperatures are going to range from 150 to 200 degrees Fahrenheit. And chlor-alkali, a lot tends to run between 180 and 200. These systems need to be analyzed formally because they're expanding and contracting. Darryl showed you some of the thermal expansion coefficients with FRP compared to steel. You know, if the systems were in steel at 200 degrees, you lay it in, typical rules, supported every 10 feet or 20 feet, have a guide every third support, and you're probably good. With FRP, it's not going to be that way. So if you're seeing leaks in your piping, in the joints, more times than not, it's an engineering problem or it's a pipe support problem. We have really good fabricators here in the U.S. Okay, I can't say that they're everywhere. We've seen some interesting things in other countries, but in the U.S., I mean, we have state-of-the-art fabricators here. The pipe and the shell, that's the most controlled part of the whole process. It's not going to have a problem, as Darryl said. It's rare. I think, I don't know, I've seen thousands of pipes. I've probably seen 2 pipe leaks that occurred. So it's very rare. So anyway, the point of all this is that when you're planning your plants, or if you have operating equipment and you're seeing leaks and it's not just wearing out after 20 years, you really need to look at the engineering concerns. Have somebody that has some background in that to take a look at these things, because a lot of times that is the root of a lot of problems. I think it was Jeff that said earlier, when there's a leak, who you call the gasket guy. If it's a elbow that's leaking, well, you call the pipe guy. But it could be the engineers that do the problem. Because unfortunately, up to recently, where really FRP is really getting mainstream in a lot of different services, a lot of your engineers, you're formally trained on metallics. I was formally trained on metallics. I was fortunate to be pulled into some Navy projects where they were doing mine hunters, and the whole vessel was either FRP or copper nickel pipe. So I learned a lot about FRP pretty early. That was back in the late 80s, I want to say. A lot of it, engineers are learning that way, but if you only see it every 2 or 3 years and you see it for 6 months at a time, you're not going to get good at it, and you're not going to necessarily understand it. That's kind of why over time, this is kind of our place. So we don't do process. We don't do a lot of steel. We have a lot of steel supports, and we connect the steel and we tie that into our analysis work. But we are where we are because this is where the greatest need is, and this is a focus where we can just focus on helping people and don't have to worry about a lot of the other things like a lot of competition and things like that, because there's just not people that know it. So with respect to markets, I mentioned a lot of them. So everywhere there's corrosion, you'll find non-metallics. In pulp and paper, in the steel industry, in the power industry, chemical processing, mineral processing, semiconductor, battery plants. Battery plants have a lot of FRP and thermoplastics going into them these days. Pretty much everywhere. So where we are today. So when I started, people would look at me, and I even looked at it in the early days. It's like, there's a lot of black magic here. I could run a lot of pipe stress analysis, but I had other people doing laminates in the background that I didn't necessarily know what was going on and why they made those choices. Over time, I learned those, but today, it's highly tested. I won't say we have everything figured out, but we have a whole lot figured out. It is an engineered product, and it is readily executed and can be repeated over and over again. But again, the key is having capable people at each place. We need capable people writing specs. We need capable people building the pipe, engineering the pipe, installing the pipe. And the same thing with tanks. And that's the key. When we know how it behaves, when we know the critical points and concerns to pay attention to, it's the execution that we have to focus on. And my recommendation, if you're buying tanks, focus on RTP1 vendors. I mean, our ASME has qualified them, and they've set the bar for performance, understanding, and execution, and documentation. So they, that's a good place. If you don't know vendors yourself, that's a good place to start. Otherwise, I would recommend that you find an SME who knows the industry and knows the vendors, ask questions, go visit them, look at the shops. You'll recognize good shops from I'll say average shops or mediocre shops. But today there is no black magic. There's, generally when you look at fabricators, what really sets them apart, I mean, there's slight things in technology, but it's execution. It's their plan and it's their personnel. You go into a shop and you look around, and the average age in the shop is probably 40 years old, and they have a lot of people there that have been there 10, 20, 25 years experience. That's probably going to be a really good shop. You look around and you see a lot of guys in their 20s, they're probably rotating out the door every other month. That's going to be a little bit concerning. And finding good personnel at all it's definitely a challenge. So these are kind of some keys. We're not perfect though. We probably wouldn't be here today if everybody was totally happy about FRP, if everybody understood it and it was all good. But I'd say a lot of it is our own making, because to a great extent, generally it works out pretty well, and we make it look simple, like, that's no big deal to go out there and weld up FRP. Oh, I fixed my boat last week, I hear a lot of that. We make it look simple, but it's not. It's all the little details in the background that, we have a system for that now. But to have laminators in the shop who have been doing over and over again with training, with supervision every day, versus hiring, say, welders out of the hall that are basically steel boilermakers a lot of times, and then training them to do FRP in a 3-day course and expecting them to do the same level of quality, it's a challenge. So what's the answer? We need more education, things like this. This is the 7th year we've done this, and we're going to keep doing it. We think there's a lot of value in it, and our focus is small, so we can kind of drill down on some of this. Some of the challenges is that pipe is pipe. We see your broad skill sets, and okay, you're an engineer, you build chemical plants all over the world, you should be able to design FRP, and it's just not always the case. So we want to make sure that we're matching the right skill sets with what we're trying to do as well. Where do we have room to grow is material selection. What I see at times is that we have vendors that are, I'll say owners, and they have vendors come in, they do presentations. They said, okay, here's my services, what would you recommend? And I have one vendor that says, okay, well, I would recommend this material. Another vendor says, here's another material. Another vendor says, here's another material. And it's kind of like good, better, best, but well, this is the cheap one. So what you don't always hear is, well, this one's good for 7 years, this one's good for 10 years, and this one's good for 20 years. Well, this one's 30% cheaper than this one over here, so if I don't know the difference, if I'm not shared that, then what am I, you know, with no other information, I pick the cheap one, right? So that kind of stuff happens. So we need to understand kind of where the sweet spots of the materials are. We don't want to run things on the ragged edge of a material surface. We want to run it at 75%. It's like going down the highway at 70 miles an hour versus 100. You know, we want it to be fast and reliable but comfortable. We don't want to be stressing that pipe out to the max every day because it's just not going to last. You know, specs. You know, NN2 is specs 5 years in the make now, and it's been out there. It's on its third revision, or going into the third revision, I guess I should say. We've had 2. It's getting mature. We're still fleshing out a few issues. We still need to work on that, but we need to also be incorporating that more into our owner specifications, our project specifications. So talking about, you know, system design, we need to look at going from designing pipe or a tank to looking at components to looking at the entire system. So we need to be looking at what are we connecting to, where are the loads. We need to be more looking at structure. Is the structure rigid really, or does it have some flexibility? We need to understand those kind of things. We need to have engineering review. So if you're an owner, well, you need to have a capable person in-house that can review those, that understands those calculations. If not, you need to find one. Inspection tools. We're an inspection company. We are looking for better tools all the time. It's a challenge. We like borescope a whole lot for piping. I mean, basically, you have to put eyes on stuff today. I mean, UT will give you thickness, but it's not going to give you a condition assessment. I think like Daryl pointed to earlier, even if you can do that, usually people want to talk about, well, this is what the corrosion barrier is on the shell, but if you see failures, all the failures, they never happen in the shell. They're happening at a manway joint, a manway reinforcement. They're happening at a bottom knuckle. You know, these are the points where failures happen. They don't happen in the middle of the shell, so UT is about useless for failure detection. So, but borescope works really good. Put a camera in there, look at it. Have an internal inspection with a qualified inspector. That really works well. But we continue to look at X-ray and other things. There's other UT out there that's developing, but we keep trying it, but we're not finding that kind of silver bullet yet. So, putting your eyes on things to do condition assessments is really the best way to do it. As kind of Daryl pointed to, you know, continued development. ASME is working on basically analysis approaches to have consistent approaches for lap joint flanges. We need to be more consistent with dual laminates. Dual laminates can be a challenge, and we just need more engineering data. Things like stress intensification factors, flexibility factors, things like that as well. Those are things that are still in the works that we need to kind of continue to develop some more. So as a whole, as I mentioned, you know, we are, you know, we're a mature industry. We've been around since the 70s, so we're around 50 years or so in now. So we don't have 100 years like steel does, but we know what we're doing. We can do good things and they can be reliable. It's just all about getting the right partners together.